The morning of December 18, 1944, near Bastogne, Belgium, Obergefreiter Klaus Hoffmann crouched in his foxhole, listening to the distant rumble of American artillery. For 2 days, his battalion had been advancing through the Ardennes forest as part of Operation Watch on the Rhine, Hitler's last great gamble in the West. The fog was thick, the snow deep, and the Americans were retreating. Everything was going according to plan. Hoffmann had reason to feel confident. Back home, Goebbels' radio broadcasts spoke endlessly of Germany's Vergeltungswaffen, the vengeance weapons, the Vone flying bombs, and V-2 rockets that were supposedly bringing London to its knees. Secret weapons that would turn the tide of the war. Advanced technology that the Allies couldn't match. The Führer himself had promised that these wonder weapons would force the enemy to surrender. But Hoffmann was about to discover that the Americans had developed their own secret weapon, one that was far more terrifying than any rocket, one that didn't announce itself with a roar or a flash. It simply killed with ruthless, invisible efficiency. The first shells arrived without warning, not the familiar whistle of incoming artillery that every soldier learned to recognize. These were different. They exploded in mid-air, precisely 20 feet above the German positions. The blast patterns were impossibly accurate. Shrapnel rained down at the perfect angle to penetrate every foxhole, every trench, every defensive position. Within seconds, 2/3 of Hoffmann's company was dead or dying. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Those who survived stumbled from their positions in what American intelligence reports would later describe as a dazed state. They had never experienced artillery like this. Traditional timed shells required gunners to calculate precisely how long a shell would take to reach its target, set a mechanical timer, and hope their mathematics were correct. Most shells exploded harmlessly on the ground or detonated too high to cause significant damage. Soldiers who had survived the Eastern Front knew how to read the patterns of enemy artillery. They knew when to take cover, when to move, when they were safe. This was something else entirely. Something that defied everything they understood about warfare. What Klaus Hoffmann didn't know, what no German soldier on that frozen December morning could have known, was that he had just experienced the variable time proximity fuse, a device so revolutionary that its development had consumed more resources than the Manhattan Project, a weapon that would increase artillery lethality by 5 to 10 times compared to conventional shells, a secret that had been guarded as carefully as the atomic bomb itself, and unlike Germany's vaunted V-weapons, which killed thousands of civilians, changed nothing strategically. This American innovation was about to fundamentally alter the nature of land warfare. To understand why the proximity fuse terrified German soldiers more than any other weapon they faced, more than Allied air superiority, more than American industrial might, more than the advancing Soviet armies, we need to understand what warfare looked like before this technology existed. We need to understand the lie that German soldiers had been told about American technical inferiority. And we need to understand the moment when that lie collided with the most lethal artillery shell ever devised. The story begins not in the Ardennes, but 4 years earlier in a British laboratory. In 1940, as Germany conquered France and Britain stood alone, a group of scientists wrestled with an impossible problem. German bombers were attacking British cities with impunity. Anti-aircraft guns filled the sky with shells, but hitting a moving aircraft with a timed fuse was nearly impossible. Gunners had to estimate the aircraft's speed, altitude, and trajectory, calculate when the shell would reach that precise point in space, set a mechanical timer, and pray their mathematics were correct. The numbers told the grim story. It took an average of 20,000 anti-aircraft shells to bring down a single enemy aircraft, 20,000 rounds of expensive ammunition, countless hours of production, all for one kill. The waste was staggering. The failure rate was catastrophic. British scientists proposed a radical solution. What if the shell itself could detect when it was near the target? What if it could automatically detonate at the perfect moment without any human calculation? The concept was elegant. The engineering was nearly impossible. A proximity fuse would need to contain a miniature radio transmitter and receiver. It would need a battery small enough to fit in a shell's nose, but powerful enough to operate the radio. It would need electronic components that could survive the most violent mechanical shock imaginable, being fired from a 5-inch naval gun. When a shell leaves the barrel of such a gun, it accelerates from 0 to 2,800 feet per second in less than 16 feet. The force is equivalent to 20,000 times the force of gravity. The shell spins at 25,000 revolutions per minute. Every vacuum tube, every wire, every component would be subjected to forces that would instantly pulverize conventional electronics. The British had a theory. They lacked the industrial capacity to make it real. In late 1940, British scientists brought their research to the United States. American industrial capacity was the key. The National Defense Research Committee established Section TT for Tuve, after physicist Merle Tuve, who would direct the program at Johns Hopkins University's Applied Physics Laboratory. Their mission was considered nearly impossible: create a rugged, reliable, proximity fuse for anti-aircraft shells. The challenge was monumental. Every component had to be miniaturized beyond anything previously attempted. Vacuum tubes had to be redesigned to survive shock forces that would shatter normal glass. A battery had to be invented that could activate instantly after firing but remain stable in storage for years. The entire system had to be small enough to fit in a shell nose alongside the explosive charge, and it all had to work perfectly, every single time. A premature detonation could kill the gun crew. A failure to arm could mean the shell landing intact in enemy territory, revealing the secret. A malfunction could waste precious resources and leave Allied ships and soldiers vulnerable. The American scientists chose radio frequency sensing as their influence mechanism. The fuse would function as a miniature radio station. When fired, centrifugal force would push electrolyte solution in a glass ampule against metal contacts, creating a battery. This battery would power a transmitter sending out radio waves at roughly 180 to 220 MHz. As the shell approached a reflecting surface and aircraft, the ground, anything solid, an interference pattern would be created. When the signal strength reached a predetermined level, a detonator would fire. The theory was sound. Making it work required solving hundreds of engineering problems that had never been solved before. The vacuum tubes were perhaps the most difficult challenge. Normal tubes would shatter instantly under the firing forces. Section T worked with Sylvania Electric to develop tubes with planar electrodes instead of the usual wire filaments. The components were packed in wax and oil to equalize stress. The glass was specially formulated to be both strong and flexible. Even the tiniest air bubble in the glass could create a weak point that would fail under stress. The battery was another seemingly impossible problem. Traditional batteries were too large, too heavy, and had limited shelf life. The solution was elegant. A small glass ampule filled with electrolyte solution surrounded by metal plates. When the shell fired, the glass broke and the acid covered the plates, generating electricity. The battery didn't need to last long, just the 2 minutes of the shell's flight, but it had to activate instantly and provide consistent power. Safety mechanisms were critical. The fuse couldn't arm until the shell had traveled far enough from the gun to avoid killing the crew. A small propeller on the fuse's nose would spin as the shell flew through the air. Only after a certain number of rotations would the arming circuit close. Additionally, if the shell was a dud and didn't detonate, a self-destruct mechanism would render it useless after a predetermined time, preventing the enemy from recovering an intact fuse. By August 1942, the fuse was ready for testing. The newly commissioned light cruiser USS Cleveland steamed into Chesapeake Bay for a 2-day evaluation. The targets were 3 radio-controlled drone aircraft. Gunners would fire proximity-fused shells at the drones, which would perform evasive maneuvers to simulate combat conditions. The test was scheduled for 2 days. It lasted less than 1. On the first day, Cleveland's guns destroyed all 3 drones with just 4 shells. The test was cancelled early. There were no more targets. The Navy immediately authorized mass production. Over 100 American companies mobilized to produce the fuses. Crosley, RCA, Eastman Kodak, General Electric, Sylvania firms large and small transformed their production lines. In Ipswich, Massachusetts, hundreds of women assembled the delicate components by hand under conditions of absolute secrecy. They were searched, entering and leaving the plant. They weren't allowed to bring purses. Even local police and fire departments were forbidden from entering the building. The women didn't know what they were building. They knew only that it was desperately important. By late 1943, American factories were producing 40,000 fuses per day. By war's end, the total reached 70,000 per day. More than 22 million proximity fuses were manufactured. The cost exceeded $1 billion in 1940s currency, roughly $15 billion in today's money. It was one of the three most expensive secret projects of the war, alongside the atomic bomb and radar. On January 5, 1943, the proximity fuse entered combat. Lieutenant Red Cochran commanded the aft 5-inch battery on the light cruiser, USS Helena, operating off Guadalcanal. 4 Japanese Aichi dive bombers, obsolete VAL aircraft, but still dangerous, attacked the American task force. One scored a hit on the New Zealand cruiser Achilles before the group broke off. As the VALs departed, Cochran's gunners fired 3 salvos of proximity-fused shells. The second salvo brought down one of the bombers without a direct hit. The shell had simply passed close enough for the radio fuse to trigger, and the blast envelope caught the aircraft. For the first time in history, a shell had independently decided the perfect moment to detonate. It was the first of hundreds of thousands of such kills. In the Pacific theater, the proximity fuse became the decisive weapon against kamikaze attacks. On May 11, 1945, the destroyers USS Evans and USS Hadley faced 156 Japanese aircraft in what should have been an overwhelming assault. Using proximity-fused shells, the 2 destroyers and a handful of fighters destroyed more than 90 enemy aircraft. The Evans accounted for 23 kills before being hit 4 times by already burning aircraft. The Hadley shot down 12. Post-action reports described the fuse as indispensable. The statistics were staggering. Against kamikaze attacks, proximity-fused shells achieved kills, with dramatically fewer rounds than conventional shells. Where previously it might take hundreds of shells to bring down one attacker, proximity fuses often achieved kills with single salvos. In some engagements, more than half of all Japanese aircraft shot down by naval gunfire were credited to proximity-fused ammunition, even though only 25% of shells fired used the new fuse. Vannevar Bush, head of the Office of Scientific Research and Development, estimated a 7-fold increase in the effectiveness of 5-inch anti-aircraft artillery with the proximity fuse. Some estimates went as high as 10-fold. But the fuse was so secret that its use on land was absolutely forbidden. Pentagon officials feared that if a shell landed intact in enemy territory, German or Japanese engineers might reverse engineer the technology. They might develop their own proximity fuses. They might develop countermeasures, electronic jamming that could render the fuses useless or, worse, cause them to detonate prematurely, killing Allied soldiers. The ban was absolute. Navy ships could use proximity fuses because shells that missed their targets fell harmlessly into the ocean. Land-based artillery was prohibited from using them under any circumstances. The first exception came in June 1944, when Germany began launching Von-flying bombs against London. The pilotless missiles approached at 400 miles per hour, making them nearly impossible to hit with timed fuses. The threat was severe enough that Winston Churchill personally authorized the use of American proximity fuses for the defense of Britain. The results were immediate and devastating for the attacking Germans. By the end of August, anti-aircraft batteries, equipped with proximity fuses, were destroying 79% of all incoming Von rockets. A weapon that had been designed to break British morale was instead being methodically dismantled by invisible American technology. The port of Antwerp, vital for Allied logistics, remained open because proximity fuses destroyed 48 of the first 75 V-1s that approached the city. But on the ground, in the fields and forests where armies clashed, the prohibition remained in force. American artillery continued using conventional timed shells and contact fuses, Soldiers continued dying at rates that proximity fuses could have prevented. Then came December 16, 1944, and everything changed. Adolf Hitler had been planning the Ardennes offensive since September. Germany was being crushed between two inexorable forces: the Soviets advancing from the east, the Americans and British pushing from the west. Traditional military logic said Germany should husband its remaining strength for defense. Hitler saw one last chance for a dramatic reversal. His plan was audacious to the point of fantasy. German armor would punch through the weakly defended Ardennes forest, drive to the coast, and capture the vital port of Antwerp. This would cut off 4 Allied armies from their supplies. British and American forces, isolated and starving, would be forced to negotiate. At minimum, Germany might buy time to deploy new weapons, negotiate a separate peace with the West, and turn all its forces against the Soviets. His senior commanders knew it was desperate. Field Marshal Gerd von Rundstedt and Field Marshal Walter Model both argued the goals were unrealistic. Germany lacked the fuel, the manpower, and the industrial capacity for such an ambitious operation. But Hitler overruled them. The attack would proceed. One element of the plan, however, was militarily sound: timing. Hitler insisted on waiting for a period of sustained bad weather. Heavy fog and low clouds would ground Allied aircraft, neutralizing the overwhelming air superiority that had made German movement nearly impossible during daylight hours. Bad weather would also make accurate artillery observation difficult. German soldiers, fighting without air support for years, had learned to use weather as their shield. The Ardennes sector was thinly held. 4 American divisions covered an 85-mile front. Some were inexperienced replacement units, fresh from training. Others were exhausted, veterans sent to the honeymoon sector to rest and refit after brutal fighting in the Hürtgen forest. The terrain was rugged, steep hills, dense forests, narrow roads, perfect for defense, but the Americans weren't expecting an attack. On the morning of December 16th, 200,000 German troops and nearly 1,000 tanks struck with complete surprise. A 90-minute artillery barrage using 1,600 guns announced the offensive. The weather was exactly what Hitler had ordered: thick fog, heavy snow, freezing temperatures. Allied air forces were grounded. German armor rolled forward, creating the bulge in the Allied lines that would give the battle its name. For 48 hours, the German offensive achieved remarkable success. American units, overwhelmed and confused, fell back. Some were surrounded. Some were overrun. The roads were clogged with retreating troops and refugees. German soldiers, many of whom hadn't experienced an offensive operation in years, felt a surge of hope. Perhaps the Führer was right. Perhaps Germany could still win. At Supreme Allied headquarters, the atmosphere was grim. General Dwight Eisenhower recognized immediately that this was Hitler's last roll of the dice. He began rushing reinforcements to the Ardennes from every available unit. Lieutenant General George Patton turned his entire Third Army, more than 200,000 men, 90 degrees, and began a forced march north through brutal winter conditions. The response was swift, but would it be swift enough? And then Eisenhower made a decision that Pentagon officials had been dreading for years. He authorized the use of proximity fuses for land-based artillery. 200,000 shells, code-named Posit, were already in Europe, stockpiled but forbidden. The prohibition was lifted within 2 days of the offensive's start. For the first time in the war, American field artillery would fire proximity-fused shells at ground targets. The first shells fell on December 18th. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Part 2. The script continues. Colonel George Axelson faced an impossible decision on the morning of December 18th. The German offensive had overwhelmed the 38th Cavalry Squadron near Monschau, Germany. The lightly armed cavalry troopers were desperate for artillery support. Axelson commanded the 406th Artillery Group. He had just received a shipment of the new secret shells, but General Eisenhower hadn't yet given explicit permission to use them. Axelson decided the emergency trumped the restrictions. He ordered his gunners to load the proximity-fused shells and fire. The German soldiers receiving that fire had never experienced anything like it. Traditional artillery followed predictable patterns. You heard the whistle of incoming shells. You dove for your foxhole. Most shells exploded on contact with the ground, sending shrapnel outward and upward at angles that foxholes and trenches were specifically designed to protect against. If you were dug in properly, if you had log-reinforced cover, if you pressed yourself flat at the bottom of your hole, you had a reasonable chance of survival. The proximity fuses changed everything. The shells didn't whistle. High-velocity artillery travelled faster than sound, so the first warning of their arrival was the explosion itself. But more terrifying than the lack of warning was what happened when they detonated. The shells didn't hit the ground. They exploded precisely 20 to 50 feet in the air, directly above German positions. The blast pattern was mathematically optimized for maximum lethality. Shrapnel rained straight down at angles that rendered foxholes and trenches useless. The fragments penetrated log-reinforced bunkers that had protected soldiers from conventional artillery. There was simply no defense. German soldiers emerged from the barrages, those who survived, in what American intelligence reports consistently described as a dazed state. They stumbled from their positions, disoriented and terrified. They knew they were facing something new, something they had never encountered before. But they couldn't understand how it worked. They couldn't develop tactics to counter it. Traditional methods of surviving artillery bombardment were suddenly obsolete. As high-velocity shells, the targeted soldiers couldn't even hear them until they exploded overhead. The sound of the shell's passage arrived after the shrapnel. Men died without warning, without chance for cover, without the psychological preparation that even a few seconds' notice provided. On December 19th, General George Patton wrote to Major General Levin Campbell, Chief of Army Ordnance, describing what his soldiers were witnessing. "The new shell with the funny fuse is devastating. We caught a German battalion, which was trying to get across the Sauer River, with a battalion concentration, and killed by actual count, 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first. 702 men killed in a single artillery concentration. The numbers spoke to a level of lethality that conventional artillery could never achieve. Patton, who had commanded artillery in World War I and understood its capabilities intimately, immediately grasped that proximity fuses had fundamentally changed land warfare. The 8th Infantry Division caught a German patrol in the Hurtgen Forest in a time-on-target mission, multiple artillery batteries firing, so that all shells arrived simultaneously. 96 Germans were found dead, every single one. The concentrated airbursts had left no survivors. German commanders began offering rewards to any soldier who could recover an intact proximity fuse. They desperately needed to understand what they were facing. American intelligence noted these orders in captured documents. The Germans knew they were up against revolutionary technology, but they had no way to analyze it without a sample. During the Battle of the Bulge, German forces did capture an American ammunition dump containing approximately 20,000 proximity fuses. Pentagon officials, learning of this disaster, went into crisis mode. American engineers had designed a jamming system. 200 jammers were hastily constructed and installed in bombers based in England, ready to defeat any German attempt to use the captured fuses. But the jammers were never needed. German engineers examined the captured fuses and concluded they were impossible. The German military-industrial complex had been working on proximity fuse designs since the early 1930s. They had developed more than 30 different prototype designs for anti-aircraft use. None had succeeded. The fundamental problem seemed insurmountable. The forces involved in firing a shell from a gun were simply too violent for any electronic components to survive. When German engineers examined the American fuses, they saw miniature vacuum tubes, delicate electronic circuits, and components that should have been pulverized the instant the shell was fired. They concluded it was some kind of trick, perhaps a decoy, perhaps propaganda material. They never recognized what they had captured. The fuses sat in the ammunition dump, unused and unanalyzed, until Allied forces recaptured the position. This German failure reveals something profound about the industrial and technological gap that had opened between Germany and the United States by late 1944. It wasn't that German scientists lacked the theoretical knowledge. It wasn't that German engineers lacked skill. It was that American industrial capacity had reached a level that Germans literally could not conceive as possible. The proximity fuse contained approximately 130 miniaturized electronic components. Each fuse cost roughly $50 in 1940s, currency expensive, but not prohibitively so. American factories were producing 70,000 of them per day by war's end. The precision manufacturing, the quality control, the logistics of assembling components from hundreds of suppliers, the entire system reflected an industrial sophistication that Germany, strangled by Allied bombing and desperately short of raw materials, could not match. German propaganda had spent years telling soldiers that Americans were soft, materialistic, incapable of true innovation. Americans could produce large quantities of crude equipment, the propaganda claimed, but they lacked the German genius for precision engineering and advanced technology. The V-weapons were supposed to prove this. Germany's rockets and jet aircraft would overwhelm American industrial production with superior quality and advanced design. The proximity fuse shattered this narrative. Here was American technology so advanced that German engineers examining actual samples concluded it couldn't possibly work. Here was precision manufacturing so sophisticated that millions of delicate electronic devices could survive conditions that destroyed German prototypes. Here was industrial capacity so vast that these expensive, complex devices could be mass-produced at a rate of thousands per day. And unlike the V-weapons, which killed civilians but changed nothing strategically, the proximity fuse was killing German soldiers with terrifying efficiency. The psychological impact cannot be overstated. Prisoner of war interrogations revealed soldiers who spoke obsessively about the airbursts. They described the attacks as quick, powerful bursts for which there was simply no defense. One German prisoner stated flatly, "There is no protection." Another described how the barrages left soldiers dazed, unable to process what had happened to them. The effect was particularly devastating at night. Traditional artillery could be tracked by sound-experienced soldiers, learned to judge where shells would fall by the whistle's pitch and duration. Proximity-fused shells arrived without warning, exploding in pitch darkness directly overhead. Soldiers had no way to estimate distance, no way to judge whether they were in danger. Every barrage became an exercise in pure terror. Communication wires, strung above ground, were cut far more easily by airbursts than by shells exploding on the ground. German units found themselves isolated, unable to coordinate, unable to call for reinforcements or retreat in good order. The airbursts cut supply lines, destroyed equipment that conventional artillery would have missed, and created casualties among personnel who thought they were safely behind the lines. The weather that Hitler had counted on as an advantage became a liability. Bad weather prevented accurate observation for timed artillery. Yes, but proximity fuses didn't require observation. They didn't require calculation. They simply worked, regardless of visibility, regardless of weather conditions. German soldiers who had felt safe from timed fire because thick fog prevented Allied spotting discovered that the airbursts found them anyway. Reports began circulating of a minor mutiny when German soldiers started refusing orders to move out of their bunkers during artillery attacks. This was extraordinary. German military discipline was legendary. Soldiers were conditioned to obey orders without question, even in the most desperate circumstances. But the proximity-fused barrages broke something fundamental. When survival was impossible regardless of training or tactics, when death arrived without warning from an invisible, unstoppable weapon, even well-trained soldiers balked. By late December, the German offensive had stalled. The weather cleared on December 23rd, allowing Allied air forces to enter the battle. But the damage had already been done. German armour, unable to advance through stubborn American defensive positions and decimated by artillery that killed with unprecedented efficiency, ran out of fuel far short of their objectives. American and British forces counterattacked, compressing the bulge from north and south. By January 25, 1945, the Battle of the Bulge was over. Germany had lost its last reserves of men and material in an offensive that gained nothing. The proximity fuse didn't win the Battle of the Bulge alone. American soldiers held key positions at enormous cost. Allied air forces, once the weather cleared, devastated German supply lines. Patton's rapid redeployment of the Third Army was a masterpiece of military logistics. But the proximity fuse multiplied the effectiveness of every artillery battery, turned near misses into kills, and created casualties that German forces could not replace. Patton would later claim that the funny fuse won the Battle of the Bulge. While this was hyperbole, many factors contributed to the Allied victory. His statement reflected the weapon's psychological impact on both sides. American commanders who had been fighting with one hand tied behind their backs suddenly had access to a weapon that fundamentally changed battlefield calculations. During the 3 months from the Battle of the Bulge to the crossing of the Rhine, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. The Luftwaffe, already depleted by years of attrition, faced a new threat that made low-level operations suicidal. The contrast with German wonder weapons is instructive. The Vone, flying bomb, and V-2 rocket were triumphs of German engineering. The V-2, in particular, was a revolutionary achievement, the world's first long-range ballistic missile, the direct ancestor of modern space rockets. The technology was genuinely advanced, the engineering was brilliant, but the strategic impact was negligible. Between June 1944 and March 1945, Germany launched approximately 9,000 Vone flying bombs at Britain. About 2,500 reached London. They killed approximately 6,000 civilians and injured nearly 18,000. The psychological impact was severe. The weapons arrived without warning, striking randomly, creating pervasive anxiety among the civilian population. But they changed nothing. British industry continued production. The port facilities the Germans hoped to cripple remained operational. The Allied advance continued without pause. And once proximity fuses were deployed for the defence of London, the Vone threat was largely neutralised. By late August 1944, 79% of all incoming V-1s were being destroyed by anti-aircraft fire. The V-2 was even less effective militarily. Between September 1944 and March 1945, over 3,000 V-2s were launched against Britain and Allied-held territory on the continent. They killed approximately 9,000 people total. The weapons were terrifying. They travelled faster than sound, so victims had no warning before the explosion. But they were wildly inaccurate, far too expensive, and impossible to mass-produce in sufficient quantities to achieve strategic effect. Albert Speer, Germany's armaments minister, would later calculate that the entire V-weapons program cost Germany approximately $500 million, equivalent to the cost of the Manhattan Project. For that investment, Germany received weapons that killed some thousands of civilians but had zero impact on the war's outcome. By contrast, the proximity fuse, at similar cost, multiplied Allied combat effectiveness across every theatre of the war. The V-weapons were offensive weapons designed to break enemy morale through terror. They targeted civilians because they couldn't hit military targets with any precision. They were propaganda tools as much as military weapons, intended to demonstrate German technological superiority and convince the German population that victory was still possible. The proximity fuse was a defensive weapon that protected ships and soldiers from enemy attack. It was a precision tool that made existing weapons dramatically more effective. It was developed in secret, deployed without fanfare, and saved Allied lives by the thousands. When it was finally revealed to the public after the war, it was simply described as one of the most important technological innovations of the conflict, on par with radar and the atomic bomb. German soldiers and commanders who survived, the war would remember the proximity-fused shells with a mixture of respect and horror. These weren't civilians cowering under rocket attacks. These were combat veterans who had survived the Eastern Front, who had endured years of Allied air superiority, who had learned to function under conditions of overwhelming material disadvantage. They recognized professional soldiering when they encountered it. One captured German officer, interrogated about the airbursts, said something revealing, "We knew we couldn't match American production, but we thought we could match American technology. We thought quality would defeat quantity. The shells that exploded in the air proved we were wrong about everything." This gets to the heart of why German soldiers hated the proximity fuse more than they feared American rockets, because the United States never needed to develop rockets for the European theater. American industrial and technological superiority was expressed not in wonder weapons, propaganda victories, but in making every soldier, every ship, every gun more effective. It was expressed in the unglamorous work of precision manufacturing, quality control, logistics, and mass production of complex devices that simply worked, every time, under impossible conditions. By April 1945, American forces were using proximity-fused bombs against German anti-aircraft positions in northern Italy. B-24 Liberator bombers dropped VT-fused bombs on flak emplacements. The batteries were immediately silenced, allowing the main bomber force to pass through unmolested. The tactical applications seemed endless. The Japanese, like the Germans, attempted to develop their own proximity fuses. They actually succeeded in creating a workable version, but too late and in too small quantities to matter. They deployed it exactly once in a dropped bomb before the war ended. The Germans never successfully deployed a proximity fuse. Despite 30 or more different designs, despite years of research, despite capturing 20,000 American samples, they never overcame the engineering challenges. The acceleration forces, the miniaturization requirements, the reliability standards, these proved insurmountable for German industry in wartime conditions. This wasn't a failure of German science or German engineering skill. It was a demonstration that by 1944, the industrial and technological gap between the United States and Germany had become unbridgeable. American factories were producing one proximity fuse every second of every day. Each fuse was tested, calibrated, and ready for combat. The logistics of distributing millions of these devices to artillery batteries across Europe and the Pacific worked flawlessly. The whole system, from laboratory concept to battlefield deployment, represented a level of industrial sophistication that no other nation could match. General Eisenhower, reflecting on the war after its conclusion, made a striking observation. It seemed likely that, if the German had succeeded in perfecting and using these new weapons 6 months earlier than he did, our invasion of Europe would have proven exceedingly difficult, perhaps impossible. He was referring to German wonder weapons, the V-1s, V-2s, and jet aircraft. But the comment reveals an interesting assumption, that German technological innovation was the primary threat to Allied success. In reality, the opposite was true. American technological innovation, expressed through devices like the proximity fuse, shortened the war and saved countless Allied lives. Admiral Lewis Strauss wrote after the war, "One of the most original and effective military developments in World War II was the proximity, or VT, fuse. While no one invention won the war, the proximity fuse must be listed among the very small group of developments, such as radar, upon which victory very largely depended." Secretary of the Navy, James Forrestal, stated, "The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater." These were not empty tributes. The statistics supported the claims. In the Pacific, where kamikaze attacks threatened to make the invasion of Japan prohibitively costly, proximity fuses reduced American casualties by factors that are difficult to quantify, but certainly reached into the thousands. Ships that would have been sunk remained operational. Sailors who would have died survived. The invasion of Okinawa, one of the bloodiest battles of the Pacific War, would have been even costlier without proximity-fused anti-aircraft protection. In Europe, the fuse's impact on the Battle of the Bulge and subsequent operations convinced German commanders that further offensive action was futile. When artillery positions couldn't be safely manned, when moving in the open meant certain death from airbursts, when no defensive fortification provided protection, the calculus of warfare changed fundamentally. The proximity fuse represents something profound about the nature of World War II. The conflict is often remembered for dramatic moments: D-Day, the Battle of Britain, the atomic bombs, but it was won through countless unglamorous innovations in manufacturing, logistics, and applied engineering. It was won by women assembling miniature vacuum tubes in factories in Massachusetts. It was won by physicists solving differential equations in Baltimore laboratories. It was won by production managers coordinating supply chains across hundreds of factories. Klaus Hoffmann, the German soldier we met at the beginning of this story, survived the Battle of the Bulge. He was captured by American forces in January 1945 and spent the remainder of the war in a prisoner camp in England. In interviews conducted decades later, he recalled the moment the airbursts first fell on his position. He remembered the confusion, the terror, the realization that everything he had been taught about artillery defense was obsolete. He remembered thinking, "This is what American technology means, not rockets for propaganda, not wonder weapons for radio broadcasts, just shells that work better than ours, just radios that are smaller than ours, just factories that can make millions of anything they need." That's how we lost the war. By war's end, more than 22 million proximity fuses had been manufactured. They served in every theatre of the war. They protected every major Allied naval operation from 1943 onward. They turned near misses into kills, saved lives, shortened battles, and demonstrated that American industrial capacity could meet any challenge the war demanded. The technology didn't end with World War II. The principles developed for the proximity fuse became the foundation for modern guided weapons. The Phoenix air-to-air missile, the Standard surface-to-air missile, the Patriot missile, all used descendants of the technology first deployed in 1943. The proximity fuse proved that a shell could make its own decisions about when to detonate. From that insight came the entire revolution in precision-guided munitions. Today, few people remember the proximity fuse. It lacks the dramatic appeal of the atomic bomb or the cultural resonance of radar. But for the soldiers who fought in World War II, both Allied troops who benefited from its protection and German soldiers who faced its lethality, it was one of the most significant technological developments of the war. General George Patton summarized it best in his letter to Army Ordnance. "I think that when all armies get this shell, we will have to devise some new method of warfare." He was right. The proximity fuse didn't just kill German soldiers more efficiently than conventional artillery. It demonstrated that warfare had entered a new era, one where electronics, miniaturization, and precision manufacturing would determine outcomes more surely than raw courage or tactical brilliance. It demonstrated that the side with superior industrial capacity and technological infrastructure would prevail, not through wonder weapons and propaganda, but through the relentless application of engineering solutions to military problems. For German soldiers in the Ardennes in December 1944, this realization came too late. They had believed in their wonder weapons, their superior technology, their advanced engineering. They discovered instead that the Americans had been quietly perfecting a device so revolutionary that German engineers examining captured samples concluded it was impossible. They discovered that American industrial capacity could mass-produce miracles, while German factories struggled to produce basics. They discovered that they had lost the technological race years before, and no amount of propaganda about vengeance weapons could change that fundamental reality. The shells that exploded in mid-air, without warning, with perfect lethality, represented everything German soldiers had been told was impossible about American engineering. They represented the moment when Nazi propaganda collided with American industrial reality. And they represented, perhaps more than any other single weapon, the inevitable outcome of a war in which one side could innovate, manufacture, and deploy revolutionary technology faster than the other side could even comprehend it was happening. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.